Welcome back to Statistical Methods. This is week 6, lecture 1, where we will be covering hypothesis tests with sample means. Now, a few announcements before we get started. Homework 3 is posted on my stat lab, and it's due next Monday, October 5th. And I also wanted to let you know that quiz 1 grades are in, and they were very positive. Overall, I believe the average was somewhere in the low 90s, around a 92, and the standard deviation was roughly 10 points. Now, last class we learned about a new kind of distribution comprised entirely of sample means, and this is called the sampling distribution of the mean. And this will serve as the comparison distribution when we want to determine the probability of obtaining a sample mean at least as extreme as ours from a distribution of sample means that's based on the null population. Now, this sampling distribution of means has a mean of its own, which is expressed as mu m, which is equal to the null population mean, or mu. Now, the standard deviation of this sampling distribution of means is expressed as sigma m, which is called the standard error and is obtained with the following formula. So, radical variance of that sampling distribution of means, or radical variance over over n, the sample size. Now, this is generally the formula that we will use. Now, we also learned the central limit theorem, which dictates that as sample size increases, two things happen. One, the variability in our sampling distribution goes down because we get more reliable and less variable estimates of the population mean, or mu, with larger samples. And further, our sampling distribution becomes more normally distributed, even if the underlying population distribution is not normal. Now, why is this important? Well, it means that we can rely upon the standard normal distribution for probability estimates without needing a normally distributed population, because these issues of normality work themselves out with larger sample sizes. So now that we know how to find the characteristics of our null comparison distribution, we're just missing one final step to be able to use null hypothesis significance testing with sample means, which is calculating a test statistic that represents our sample means extremity with reference to this comparison null distribution. Now, this is exactly what we did before with z-scores, calculated as a score minus a mean divided by that sample's standard deviation. Now, note what this statistic captures: the extremity of an individual score with regard to the mean and standard deviation of a null distribution of scores. Now, we want to do the same thing, but gauge the extremity of our observed sample mean with regard to the mean of the sampling distribution of means and the standard deviation of this null distribution of sample means. So the statistic we will use to do this is also referred to as a z-score, since we'll be still trying to rely on this standard normal distribution. But the calculation is slightly altered from before. Now, previously, the z-score was based on an individual score. So z equals x, or an individual score, minus m, the sample mean, divided by the standard deviation. Now, the z-score will be based on a sample mean. So the sample mean minus the mean of the sampling distribution of means, divided by the standard error of the mean, which is, again, the standard deviation of the sampling distribution of means. So for example, let's say that I recorded the height of 50 women and obtained a sample mean of m equals 66 inches. Now, let's say I know that the general population distribution of women's heights in the US has a mean of 64 inches with a standard deviation of 3. Now, using the formulas we learned last time, I can obtain the characteristics of the sampling distribution of the mean for samples with n equals 50 women. Now, that mean of the sampling distribution of means here is 64, as expressed above, the same as the population. Now, the standard deviation is radical variance divided by n, or standard deviation divided by radical n. Now, in this case, the standard deviation is 3, expressed right here, and n, the sample size, is 50. So 3 divided by radical 50, which equals 0.42. Now, let's calculate the z-score. So our sample mean is 66 inches. The mean of the sampling distribution of means, or this null comparison distribution, is 64. So our sample mean minus the comparison mean divided by 0.42, which is that standard error of the mean. So we have a pretty large z-score, 4.76. Now, with the z-score based on a sample mean, we can now ask questions about how likely obtaining a sample mean this extreme would be if the null hypothesis were true. In other words, exactly what we did before, but now z-scores give us extremity of means, not individual scores. Now, this type of hypothesis test we conduct in these situations, so asking probabilistic questions about a sample mean when the null population mean and variance are known, is called a z-test. Now let's work through an example of a z-test for a sample mean using the same 5 steps of null hypothesis significance testing we learned earlier. So a developmental psychologist wants to compare homeschooled children and public school children on a measure of social reasoning and empathy that is scored on a 0 through 100 scale. Now let's assume that we know the following information about the distribution of empathy scores for public school children, so the population. And on this scale, they have a mean of 60 and a variance of 20. Remember, sigma squared is variance. Now our psychologist hypothesizes that his sample of n equals 45 homeschool children will have different scores on this measure than public school children. So step 1 is to restate the question as a research hypothesis and null hypothesis about the populations of interest. So in this case, the research hypothesis would be that the null population of homeschooled children will have a different empathy social reasoning score than the general population of public school children. In other words, the mean of homeschool children on this empathy reasoning measure will be different, or in other words, not equal to, the mean on this measure for public school children. And the null hypothesis would be that these two populations do not score any differently on this empathy social reasoning measure. Or in other words, the mean of homeschooled children is the same as the mean of public school children. Now, step 2 is to determine the characteristics of the comparison distribution. So we need the mean of the sampling distribution of means, and we need the standard error of the sampling distribution of means, which is the standard deviation, and the overall shape of the sampling distribution of means. Now, the mean of the sampling distribution of means is easy. It's the same as the mean for the population of public school children on this measure, which earlier we found to be 60. Now, we also had a variance of 20. So the standard error, again, is radical variance over the sample size. So in this case, radical 20 over 45. So our standard error here is 0.67. Now, since the sample size is larger than 30, we know that our sampling distribution of means is normally distributed because of the central limit theorem. Now, step 3 is to determine the cutoff score on the comparison distribution at which the null hypothesis should be rejected. Now, this researcher decides to use the standard cutoff of p is less than 0.05. Because our comparison sampling distribution is normally distributed, and we want to conduct a two-tailed test, we look up the z-score that isolates 2.5% of scores in both tails, which is, as we learned last time, positive or negative 1.96. Now, it's a two-tailed test because we're not making any directional hypotheses about the difference in scores on this measure between homeschooled and public school children. We're only stating that there is going to be some difference. So that is a two-tailed test. Now, step 4 is to determine your sample's score on the comparison distribution. So the researcher collects data, tests his 45 homeschooled children on the social reasoning and empathy test, and then computes the sample mean of 61. Now, what's our z-score? Now, 61 is our obtained sample mean, and we're subtracting from that the population mean of public school children of 60 and dividing by that standard error, which we calculated earlier, 0.67. So our z-score is 1.49. Now, step 5 is to simply decide whether to reject the null hypothesis. Is our z-score more extreme than the cutoff sample score? Well, let's see. So our z-score is 1.49 versus our cutoff of 1.96. No. So we failed to reject the null hypothesis here. In other words, is there less than a 5% chance of obtaining a score as or more extreme than ours if the null is true? The probability of finding a z-score that is as or more extreme than 1.49 in a standard normal distribution is p equals 0.136, which is greater than 0.05. So we failed to reject the null hypothesis. In other words, these findings are inconclusive. We can't say whether or not there is a difference on this empathy reasoning measure between public school kids and homeschooled kids. Now, that's all for this lecture. Continue with the scheduled readings for Wednesday and begin working on homework 3, which is due Monday. Now, just as an update, I am grading homework assignments for completion throughout the course, so as long as you put in a good faith effort, you'll receive credit. Thank you.